Hello there. In this lesson, we're going to explore buffers, which you can make with weak acids and their conjugates, or weak bases and their conjugates. So buffer is a solution that has a mixture that keeps the pH pretty much the same, regardless of whether you add acid or base to it. So with water, if I add a little bit of acid to that, it's going to make it very acidic very quickly. The water might dilute it a bit, but it's still going to be pretty acidic pretty fast. And the same thing if I add some base. But with a buffer, the pH stays pretty much the same, at least for a while, when you add acid or base. So we're going to look into what's in the buffer and how it does that neat little trick. So buffers have applications in many different areas and many different solutions, but the one that I find the most compelling is in the fluids of your body, like blood. So blood pH has to be kept in a very narrow range in order for red blood cells to be able to function properly and happily carry oxygen to and from your body cells. The proteins that do that, like hemoglobin and others, have to be the right shape. And if you go outside of that range, then those proteins start to change shape and not function so well. So if you add base and you start to get at the high end here of the pH scale, then the function will decrease until eventually the cells die. And same thing at the low end, if you add acid, the function will decrease and eventually death will follow. So that's why buffer is what's needed, so that added acid or base can be neutralized and the pH be maintained at an optimal level. So to make a buffer, you need two ingredients. One is you need a weak acid of a certain concentration. In the case of our blood pH buffer, it's carbonic acid. So carbonic acid's a weak acid. And if you just have carbonic acid, well then, because of the low value of the constant, you're only going to have a little bit of the conjugate base. So this is where a buffer is a little bit different, because a buffer is going to have an elevated or roughly equal concentration of the conjugate base of the acid. You can also make buffers with weak bases and their conjugates, but the one in our blood uses a weak acid. So you've got carbonic acid as the one ingredient, and the other ingredient is roughly equal concentration of the conjugate base. So one mistake that I often see students make, that I should mention at this point, is that these two components are still opposing each other on opposite sides of the equilibrium, right? The acid is still going to donate a proton and become its conjugate base. It's just that you're going to have roughly equal amounts of these two. And even though you might add externally some of this conjugate base, it doesn't mean that it's another reactant that's going to go on the same side of the equilibrium arrow. So a graphical representation of the difference between a buffer and a weak acid is what we have here. So weak acid would have a fairly high concentration of the acid compared to the conjugate base being very low. So that's what you get if you just have like vinegar or carbonic acid or any of those weak acids. Very little of the conjugate base would actually be present in the solution. So to change that to a buffer, what you have to do is add a roughly equal concentration of the conjugate base so that they're pretty much equal on either side of this equilibrium. So that's the trick, adding extra conjugate. And so you can do that just by taking a salt that has that conjugate in it and throw it into the solution. So here's a situation where you're starting off with 100 milliliters of 0.1 molar carbonic acid. So let's figure out how many moles of acid that is. H2CO3. So we got 0.100 liters, and we're going to multiply that by the concentration, 0.10 moles for every liter, and gives us 0.01, whatever, how many zeros you need, moles of the acid. So now what we want to do is have that same concentration or same number of moles of the conjugate base in there. And a conjugate base we're using is this sodium bicarbonate. So we are going to figure out the mass that is required for that. And we're going to use the same number of moles so that we end up with equal concentrations. So moles of, this time we want HCO3 minus, And so of course there's only one HCO3 minus for every one NaHCO3, and then the molar mass, let's look that up. The molar mass is 84 grams per mole, and so that means we're going to need 0.84 grams of the baking soda to balance out the same number of moles of the carbonic acid. So once we have them equal, then we have ourselves a buffer. So now we have this buffer solution here in the one beaker that has acid, and base. Well, conjugate base. But they're in pretty much the same concentration now. So that means that if I add some acid, that the pH of the buffer stays the same because this conjugate base neutralizes that acid. And the same thing happens when I add some base. Here's some sodium hydroxide being added, and you can see that the acid part of the buffer kept the pH pretty much the same. The color stayed pretty much the same. When the acid and the base were added to water that doesn't have the buffer system in it, you can see that the water here becomes more pink, so it's now acidic. And you see the water here became more purple, which means it's now a base. So neutralization is the main function of a buffer. If acid is added, it'll neutralize that. If a base is added, it'll neutralize that. It neutralizes either way. And so neutralization is what you call quantitative. That means that there's no equilibrium back and forth. The reaction just goes all in one direction and everything gets consumed. So if you add acid, the conjugate base will react with it. And it's kind of like you're replacing this strong acid that's being reacted with the weaker one that will be the product of the neutralization. Same thing happens when you add base. It'll react with the acid part of the buffer, and you'll replace it with the weaker conjugate base that gets produced. So there you go, both of them being neutralized. All right, so calculation time. Let us determine the pH of this buffer before we start adding acid or base to it. And so this is just like any weak acid calculation. Of course, it's an equilibrium, so we're going to have a constant, and the constant is going to be equal to the hydrogen ion concentration times the conjugate base concentration here all over the weak acid concentration. So in our question down here, we're given 3 out of those 4. We have the constant, which is 4.3 times 10 to the negative 7. The hydrogen ion concentration, that's what we need. And the hydrogen carbonate concentration is 0.39 moles per liter. And our carbonic acid concentration is 0.45 moles per liter. So we'll rearrange this. So we get our H plus concentration. That's going to be the 0.45 moles per liter times the Ka times 10 to the negative 7 divided by 0.39 moles per liter. And we'll work that out. I'll pause. So it's 5.0 times 10 to the negative 7 moles per liter for the hydrogen ion. And then, of course, for the pH, it's the negative log of that, 5.0 times 10 to the negative 7. And that works out to be 6.3. 6.3. There we go. pH of our buffer. Alrighty, so now we're going to look at a buffer in action when neutralizing some added acid. So I like to start with a little ice table. We're going to put our acid down here first, and it's going to react with the conjugate base of the buffer. So we got HCO3, and then that's going to produce the carbonic acid, H2CO3, by giving the proton, and there'll be some chlorine ions left that we won't bother with because they're not really part of the buffer. So again, remember that this is a quantitative reaction. It's going to go into completion, so one of these components is used up. Because we have 1 liter, it's easy to convert all these things into moles. And for most of these things, you could leave them as moles because to put them into a concentration, you're going to always be dividing by the same volume. And so it's an extra step that you don't necessarily have to do. If you do, it's fine. But I'm going to leave it out here just because I think it makes it a little easier to follow when it's just moles. Right, so let's put the values in. Our number of moles of the conjugate base here is 0.65 to begin with. We're adding in 0.05 moles of the acid. And to start with, we have 0.75 moles of this acid that is being produced afterwards. So the reaction is going to go to the right, right? We're going to use up some of those two, and we're going to gain some of this, and who cares about the chlorine? And so obviously the HCl here is your limiting reagent. It's going to go to 0, which means your X is 0.05. And so 0.65 minus that is going to be 0.60 moles of the hydrogen carbonate. And this is going to go up by X, so it means we're up to 0.80 moles of the acid. So these are the two pieces that you need in order to solve for the pH, just like we did before. So we can put that over here. The Ka, of course, equals hydrogen ion times the conjugate base all over the acid, right? So if we rearrange that to get the hydrogen ion, it's going to be the Ka times the acid concentration all over the base concentration. Now, because, again, these are in the same volume, we can use moles here because if this is in moles per liter and this is in moles per liter, well, the liters will just cancel out, so it doesn't really matter if you include the volume at all. So I'm going to use moles. You can include, if you want to divide by 1 to get the moles per liter, you'll get the same answer. So let's put our values back in here. We got 4.3 times 10 to the negative 7. We're going to multiply this by the acid part, which is this guy, 0.8 moles per liter, or moles, and then divide that by the 0.6 moles for the conjugate base, and let's see what that comes out to. So it's 5.73 times 10 to the negative 7 moles per liter, and of course if we want the pH equals negative log of that hydrogen ion concentration, which equals 6.2. 6.2. Yay! So that second part of the process where we're determining the pH involves rearranging the equilibrium constant equation pretty much in the same way every time. And so this Henderson-Hasselbalch equation does that for you. So I'll show you how that works with neutralization with a little bit of base this time. So let's take that same buffer, and this time we'll react it with a base. So we've got strong base, so we'll put in some OH minus ions here, and that's going to react with the acid, right, in the buffer. So H2CO3 is our acid, and again it's quantitative, so all the way, and that's going to give us some carbonate ions, hydrogen carbonate ions, and some water, right, because it's going to neutralize it. And so what we're going to start with here is 0.06 moles of the base being added, and we had 0.75 moles of this acid and 0.65 moles of this conjugate base. And who cares about the water? It's a liquid anyways. So this is going to get all used up, and the same amount is going to get used up for the acid, and equal amount being produced for the conjugate base. And so you're going to end up with this being 0, of course. You're going to take away 0.6 from this side, so we're down to 0.69 moles of the acid, and we're going to add the 0.6 over here, so we'll end up with 0.71 moles of this conjugate base. Great, so now we got these new number of moles, or concentrations if you like, and we're going to put that into our newly rearranged Henderson-Hasselbalch equation. So you see that the Henderson-Hasselbalch has this pKa value that you probably haven't seen before, but it's pretty straightforward to use. All you do is take the negative log of your Ka. So just like pH was negative log of the hydrogen ion, pKa is negative log of the Ka. And then we're going to add the log of the concentration of the base, conjugate base, all over the concentration of the acid, right? Concentration, nice square brackets there. So let's put in some numbers. So negative log of the Ka, which is 4.3 times 10 to the negative 7, plus the log of A minus, which is our 0.71 moles, all over, it's like a ratio here, 0.69 moles of the acid. So I'm going to put that in my calculator. Okay, so for the negative log of the Ka, we get 6.37. And for the log of this fraction here, we get 0.012. And then if you add those up, you get 6.38. And I guess with sig figs here, we pretty much end up with 6.4. So there you go, pH using the Henderson-Hasselbalch equation. Alrighty, now lastly, we can get really fancy with our Henderson-Hasselbalch equation and recognize that when you add acid or base, the moles are going to change the same to the conjugate and to the weak acid present in the buffer in equal but opposite ways. So if you add a base, well, then the acid is going to be decreased by the amount of base that is added, and the conjugate base is going to be increased by that same amount. And if you add an acid, well, the base is going to be decreased by the amount of acid added, and the acid part is going to be increased by that same amount. So if you can keep these equations straight in your head, you can use them and get around the ice table process that I showed you earlier. I like ice tables anyways, just because I've been using them since the beginning with all of our equilibrium stuff. But if you're an equation or a formula type person, well, this might be right up your alley. So let's try it out with this last one here when we are adding some acid again. So let's put the values in to this guy here. So pH equals the pKa. It's the same acid, so the pKa from last time was 6.37, and we're going to add the log, and then we'll just put moles for everything. So we have a buffer with this many moles. Oh, of both, okay. So we have 0.50 moles of the base and the acid. So the base is going to lose the amount of acid added, which is 0.07 moles of the acid. And then the acid is going to gain that same amount. So we're going to have 0.50 moles of this, and plus the amount of strong acid added. And so then that's 6.37 plus the log, and then we'll work these values out. I'll take away 0.7, so that's 0.43 moles on the top. And on the bottom here we got 0.57 moles. And then we'll put that in my calculator. So we end up with the 6.37, and then we're going to add, and then the log of that fraction turned out to be negative 0.12. The rest, I guess, doesn't matter. And so then, to finish this off, we are going to subtract that. 6.37 equals, and we'll end up with 6.25 as the pH. So there you go. So that might be a shortcut for you if you like the formula. If not, you can do it the two-step way that I showed you earlier. So with a little practice, you'll be buffer masters before you know it. See you soon.